So this is the cis and trans isomer with the same molecular formula, same structural formula, but different arrangement in space due to limited rotation across the double bond. Now, let's see some more examples. Let's see this. So if we have this right here, let's see this. Let's name this first. Can you name this for me? First, we will pick what? The longest chain or the parent chain. 1, 2, 3 carbons. So the longest chain is 3 carbons. And on carbon number 2, we have a methyl group. We will number the carbon such that the alkene gets the least number. So this is carbon 1, carbon 2, carbon 3. On carbon 2, we have a methyl. This is what? 2-methyl prop 1-ene, right? Now, this right here is 2-methyl prop 1-ene. Let's see the criteria. Does it fulfill the 2 criteria we need for cis-trans isomerism? The first criteria is you need a carbon-carbon double bond. Does this have a carbon-carbon double bond? Yes. Then each carbon must have 2 different atoms or groups attached. Does this have 2 different atoms or groups? No, they are both CH3. And on the other carbon also you have both H's. Both carbons must have different atoms or groups attached to it. And since this does not fulfill both the criteria, this will not show cis-trans isomerism, right? So this does not show cis-trans isomerism, right? So, so this does not show geometric isomerism. Is this clear? Is this clear? Let's see another example. If we have this, can this show cis-trans isomerism? So the first criteria is carbon-carbon double bond. On each carbon, you must have 2 different atoms or groups. Are they both different? Yes. Let's look on the other carbon. The other carbon has a HCH3. Are they both different? Yes. So since both the atoms or the groups of atoms attached on each carbon are different, this can show cis-trans isomerism. Yes. And now, which isomer is this? Is this the cis or the trans? This will be the cis isomer because similar atoms are on the same side of the molecule. So this will be what? Cis but 2-ene. Do you see this is butene or but-2-ene? This is the longest carbon chain. On carbon number 2, we have a double bond. Yes. So this is but-2-ene. But which isomer is this? The cis but-2-ene. Can we draw the trans for this? How will we draw the trans? How will we draw the trans? Where similar groups are on opposite sides. So this will be what? Trans but-2-ene. Clear? So this is cis but-2-ene. This would be what? The trans but-2-ene. So here, similar groups are on opposite sides. So this is trans but-2-ene. Is this clear? Can you try to make the cis-trans of the other examples that I'm just going to write down? Hold on. All right, so let's see number 3. For number 3, you have a carbon-carbon double bond. So the first criteria is met. On this carbon, you have a CH3 and a C2H5. Are they both different? Yes. On this carbon also, are they both different? H and CH3? Yes. So can this show cis-trans? Yeah. Now, which one will be the one that we've drawn? Will this be cis or trans? Cis. Because similar groups, which are the 2 CH3s, you see similar groups on the same side. So similar groups are on the same side. Therefore, this will be the cis isomer. Yes. And if you name this, what will this be? So the longest chain is 1, 2, 3, 4, and 5. So the longest chain is 5. and you will number your carbon atoms in such a way that the alkene gets the least number. So you will number from this side 1, 2, 3, 4, and 5. So this will be what? 3-methyl pen-2-ene. So this is what? Cis 3-methyl pen-2-ene. Clear? Understood? Now let's draw the trans isomer for this. What will be the trans? So the trans will be where the two CH3s are on opposite sides. Yes? So if the two CH3s are on opposite sides, we call it the trans isomer. So this right here is the trans isomer. Clear? Because the similar groups are on opposite sides. Understood? Let's see number 4. In number 4, we have a carbon-carbon double bond. So the first criteria is met. Now, if you look at the first carbon, it has a CH3 and an H. Are they both different? Yes. Look at the other carbon. It has a Br and a Cl. Are they both different? Yes. Can this show cis trans? Yes. Now, you will be like, it can show cis trans because it fulfills both the criteria. But we don't have similar atoms here. So how do we identify the cis and trans? In such a case where you do not have similar atoms, you pick the heavier atoms on each group. On this group, on each carbon, I mean. On this carbon, which is the heavier group, H or CH3? CH3, because it has more mass, yes? Between these two, which one is heavier, Br or Cl? Br. So if heavier groups are on the same side, what are the heavier groups? The ones with greater MR. So if they are on the same side of the molecule, then it will be what? Then it will be what? The cis isomer. And if heavier groups or the ones with greater MR are on opposite sides of the molecule, then it is the trans isomer. Is this clear? Yes. Now if you see this, Br is heavier, CH3 is heavier. Can we call this the cis isomer? And what will be the trans for this? The trans isomer would be Br and CH3 are on opposite sides. Yes? So if they are on opposite sides, this will be the trans isomer. Is this understood? Clear? Now let's see properties of cis-trans isomers. Yes. So let's name this. Let's pick the longest chain. How many carbons do we have in the main chain? 2, 3 actually. 1, 2, 3. Yes? Clear? Now you have halogens on carbon number 1. Yeah? And you have alkene also on carbon number 1. So this is your longest chain on carbon 1, 2, 3. On carbon 1, we have a bromo and a chloro. So what will we call this? 1 bromo. Because you always name halogens first and you name them in alphabetical order. B comes before C, so bromo will come before chloro. So this will be 1 bromo, 1 chloro, prop 1 ene. So this is cis 1 bromo, 1 chloro, prop 1 ene. Understood? Yes? Is this clear? Is the naming clear? Yes? All right. Now, let's see the properties of these. That will be the trans 1 bromo, 1 chloro, prop 1 ene. Clear? Now, let's see the properties of these isomers. Let's see the properties of cis-trans isomers. So let's see the properties of geometric isomers. Now, let's see the properties. So since the cis and trans, they have difference in arrangement. Yes, the arrangement of atoms is different. In cis, similar atoms are on the same side of the molecule. In trans, similar atoms are on opposite sides of the molecule. So that will be the difference between these two, and let's see how that affects the properties of these isomers. So let's see an example. We have C double bond, let's take HCl, HCl. So this is going to be the cis isomer. So this is cis 1,2 dichloroethene. Yeah. And then let's see the trans. The trans would be where the H's are here, the Cl's are on opposite sides. So this is cis 1,2 dichloroethene. And this is trans 1,2 dichloroethene. Yes? Now, let's see what will be the difference in their properties. If you see the cis isomer, let's make the dipoles, right? Now, between carbon, hydrogen, and Cl, which element is more electronegative? Chlorine. Because if you remember, FO and Cl were the most electronegative. So Cl will be partial negative. The carbon and the hydrogen are partial positive. So if we were to make a dipole, it would be from carbon to Cl, from carbon to Cl. Yes? Here, this is partial positive, partial negative, and partial negative here. Yes? There will be an arrow from carbon to chlorine and from carbon to chlorine like this. Now, in trans, if you see the dipoles are going in opposite direction. Yes? Do you see a dipole going upward and a dipole going downward in opposite direction? So in trans isomer, the dipoles are in opposite direction, so they can kind of cancel out, not entirely, because the molecule is not symmetric. Do you see? The molecule is asymmetric, it's not symmetric, therefore the dipoles do not cancel out completely, but still the resultant dipole will be weak. Yes? Or you can just, for the sake of this question, you can just say the dipoles cancel out because they're in opposite direction. Yes? So the dipoles are in opposite direction. So this will have a weak net dipole. Yes? Or can I say this will be non-polar because the dipoles cancel out? Yes? So since the dipoles are in opposite direction, this would be what? Non-polar, as the dipoles cancel out. Yes? So since the dipoles cancel out, it will be non-polar. On the other hand, this right here, the dipoles do not cancel out. Do you see that? And they're going downwards. Both the dipoles are facing downwards. So the dipoles do not cancel out. There is a net dipole. Yeah? So there is a net dipole acting downwards. And since there is a net dipole, this will be a polar molecule. Yes? Because it has a resultant or a net dipole or a dipole moment. Yeah? So since this is a polar molecule, this will have stronger intermolecular forces. And since this is a non-polar molecule, it will have weaker intermolecular forces. Because this will only have van der Waals forces which are induced dipole forces. Yes? And on the other hand, this will have what? Permanent dipole forces? Yes? I'm naming the stronger one. Alright? So this will have permanent dipole forces. So since this has a stronger intermolecular force, can I say this will have a greater boiling point? And this will have a lower boiling point. So the cis isomer from the trans isomer can be differentiated how? On the basis of their boiling point. The cis isomer will have stronger intermolecular forces, therefore a greater boiling point, as opposed to the trans isomer. So this is how you differentiate between them. Cis and trans can be differentiated on the basis of, they can be differentiated on the basis of their, it can be differentiated on the basis of their boiling point. Yes, the cis isomer is what? The cis isomer is polar and is therefore going to have a higher boiling point compared to the trans isomer. So the trans isomer is non-polar, right? Because the dipoles cancel out, and this will have a lower boiling point. Clear? Is this clear? All right. Let's have you try this question. You have for this? 4. Let's see. So we have draw all possible structural and stereoisomers of C4H8. So let's see. So C4H8, they've told you to make alkenes only. So in structural, you will not include the functional isomers. All right. So let's draw the first one. So you make a straight chain butene. Yes. And let's name this. So this will be but1ene. Then you make another straight chain, change the position of the double bond. So this becomes what? but2e. Yes. Then can we have a but3ene? No, because when you make a but3ene, that will be the same thing as but2e, right? Then you shorten the chain. You shorten the chain and you make a prop. And let's put the 4th carbon on carbon number 2 here. You can't put it on terminal ends. So you put the CH3 here, and this will become what? 2-methyl prop 1ene. Are there any other possibilities in terms of chain and positional? No. Now, if you see right here, you got to also include stereoisomers. You know, if you have a carbon-carbon double bond, there could be geometric isomerism or cis-trans isomerism. Let's look at this. Can this show cis-trans? You have a carbon-carbon double bond, but this one has 2 hydrogens. So this can't show cis-trans. Yes, because both carbons must have different atoms or groups attached to it. So you don't even have to bother to look at the other one. When the first one can't, you don't need to bother. In the second one, but2ene. If you see, this is the carbon-carbon double bond. You have the double bond, yes. This one has a HCH3. Are they both different? Yes. This one also has a HCH3. Are they both different? Yes. So will this show cis-trans? Yes. This will have not 1, but it will have how many isomers? 2. It will have cis-but2ene and it will have trans-but2ene. Now, but2ene is not separate. All right. You won't be like, oh, there are 5. But1ene, but2ene, cis-but2ene, trans-but2ene. No. But2ene can either be cis or trans. So this is your 1 isomer, your 2nd isomer, the 3rd, and this will be the 4th. Is this clear? So there are a total of 4 isomers, including structural and stereoisomers for C4H8, which are alkenes only. Clear? Let's have you try this. Again, the same thing. Try it for C3H4Cl2. First, you make the structural, and then once all the structural isomers are complete, then you see which ones can show cis-trans. If you see, the general formula here is 3 carbons with 6 atoms attached to it, 4 hydrogens and 2 chlorines. So the general formula is CnH2n. Again, you got to make alkenes only, no cycloalkenes. All right, try it. All right. So C3H4Cl2. Now there's definitely a double bond, yeah, because it's C3 with 6 atoms attached to it. So it's the same general formula CnH2n, yeah. Besides, all atoms attached are not hydrogen. So let's see the first isomer. So what we'll do is we will make this. Now you can't shorten the chain. We know that. And changing the position of the double bond is not a possibility either. Because even if you put it on the other carbon, it will still be counted as carbon number 1. Clear? Either you put it here or you put it here. Either way, it's carbon number 1. Now you put both the Cl's here. This is what? 1,1 dichloro-propene. Yeah? Then we can have 1,2 dichloropropene. You can't have 2,2 dichloropropene. Do you understand that? Then you can have 1,3 dichloropropene. Yes. So this is 1,3 dichloropropene. Then 1,3, then you can have 2,3 dichloropropene, because you will number your carbon atoms such that alkene gets the least number. So you will give this carbon 1, carbon 2, carbon 3. Clear? Then we can have this. Then we can have what? Carbon 1. We can have both the Cl's here. This is carbon number 1, 2, 3. What is this called? 3,3 dichloropropene. Yes. So you've made all the chain and positional isomers. We can't have chain isomers really, but yeah, you get the point. Now we got to look for stereoisomers. Can this show cis trans? No. Why? Because the first carbon has 2 Cl's. They need to be different. Are they different? No. This can't show cis trans. Can this show cis trans? This one has a Cl and a H. This one has a Cl and a CH3. Yes, this can show cis trans. So this won't be one isomer. This would be a cis and a trans. Yes. Let's look at this. This one has a Cl and a H. H and this, are they both different? Yes. Yeah. Therefore, this can also show what? Cis and trans. Then this one cannot show cis trans because the carbon has 2 H's. Then this one also cannot show cis trans, the carbon has 2 H's. So how many total isomers? Let's count. We have 1, 2, 3, 4, 5, 6, and 7 total isomers. Is this clear? Do you guys understand this? Do you all get it? Yes? Kids online, is this clear?